Today let's discuss questions related to double integral, and it is one of the important topics in calculus, as almost every year at least one question is asked from this topic. So let's start with questions. Also, like in questions involving double integral and triple integral, it's better to first draw the figure of an area that we're supposed to evaluate. So that basically helps us make better decisions, and helps us better interpret the integral that we are supposed to solve. So let's get started. So the question 1 says that use double integration to calculate the area common to the circle this and the parabola. So in this question we're supposed to find out the area that is common to this circle and the parabola. So first thing is, let's just draw the figure of the circle and parabola and see what area is common in between them. So if you see that equation of circle is x square plus y square equals to 4. So its center is 0, 0 and radius is 2 units. So circle will be somewhat like this, and this point is 2, 0 and here it is minus 2, 0. And the parabola is y square is equals to 3x. So its vertex is also 0, 0, so it will be somewhat like this. And we are supposed to evaluate basically the common area of circle and the parabola. So I'll just shade the area that is common in between parabola and circle. So we are supposed to find the area of this shaded region. So to find out that, first let us find out the point of intersection of the circle and the parabola, that is this point A and this point B. So let's just calculate area, basically the point of intersection. So if a circle and parabola are intersecting, then x square plus y square is equals to 4, but my y square from equation of parabola is 3x. So we'll plug in this value of y square here in equation of circle to reduce it in quadratic form in terms of x. So it will be x square plus 3x is equals to 4. Now let's just solve this equation and see what so that will basically gives us coordinate of x-axis, like x coordinates of intersection point. So I can write it as minus x minus 4 equals to 0, x plus 4, and if I pull out minus 1 it will be x plus 4 equals to 0. So from here it is x plus 4 times x minus 1 equals to 0. So these both of them intersect at when x is equals to minus 4 and x is equals to minus 1. So we got these two values of x. Now let's just find out value of y by plugging in these values in the equation of parabola. So when x is minus 4, y square is equals to 3 times x, that is 3 times minus 4, which is minus 12. But in real line we cannot have square as negative, so we'll just discard this option. So let's see what is value of y when x is equals to 1. So y square is equals to 3. So that basically gives us y as plus minus under root 3. So the intersection points are A, that is 1 comma under root 3, and B, that is 1 comma minus root 3. So these are my intersection point, 1 comma under root 3 and B, 1 comma minus under root 3. Now we are supposed to find out the area. So if you observe that, like till this point, this is the parabola is the curve if I calculate area of this region, and after this point the curve is basically circle in this region. Also the figure is basically symmetric around over x axis. symmetric over x axis. So it's enough to find out area of this region, like above the shaded region above the x axis, and then we'll multiply it by 2 to get the area of whole shaded region. So let's just solve it. So shaded region is area of shaded region will be equals to 2 times of area of when x is varying from, if you see that in this, x is varying from 0 to 1 and y is varying from 0 to this, that is under root 3x. So x is varying from 0 to 1 and y is varying from 0 to under root 3x into dy dx, plus here x is in this region, that is in this region, x is varying from 1 to 2 and y is varying from under root 4 minus x squared to 0. So it is 1 to 2 and y is varying from 0 to under root 4 minus x squared dy dx. So let's just solve in this integration to find out the area of shaded region. So it will be 0 to 1 under root 3x dx plus integration 1 to 2 under root 4 minus x squared dx. Now if we just solve it, it will be 2 times of under root 3 x raised 3 by 2 divided by 3 by 2 and limit varying from 0 to 1 plus x by 2 under root 4 minus x square plus 4 by 2 into sine inverse x by 2, and in this case my limit varies from 1 to 2. Now let's just plug in the limits and see what is the final value of area. So it is under root 3 into 2 by 3 into 1 plus this will be 0, 0 plus 2 sine inverse 1 minus, when I plug in 1 it will be 1 by 2 under root 3 plus 2 times sine inverse 1 by 2. Now let's just solve in these values. It will give us 2 times 2 by under root 3 plus 2 into sine inverse 1 is basically pi by 2 minus under root 3 by 2 minus 2 sine inverse 1 by 2 is pi by 6 basically. So it will be pi by 6. Now if we just simplify it, it will be 2 times 4 minus 3 divided by 2 under root 3 plus pi minus pi by 3. So it reduces to 2 times 1 by 2 under root 3 plus 2 pi by 3, that is equals to 1 by root 3 plus 4 pi by 3. So this is basically the required area that we are supposed to find. So let's move on to the next question. So the next question says that evaluate this integration over the region R, and the region R is basically they have defined as is the region in first quadrant bounded by the hyperbola xy equals to 16 and the line y equals to x, y equals to 0 and y equals to 8. So they have defined us a region R, and over that region we are supposed to evaluate this given integral. So first let's just draw the figure and see what is the region R. So if I draw, let's say this is my x, this is my y axis, this is my x axis. So parabola xy equals to 16 will be somewhat of this form, and here as well another line is line y equals to x, that will be this line y equals to x and y equals to 0, x axis acts as y equals to 0 and x equals to 8. Let's say our x equals to 8 lies somewhere here. So x equals to 8 and R is the region bounded by all these figures. So if you observe that the region that I am just coloring with red color is the required region R. So this region is R, and we need to evaluate our integral over this region. So let's do that. So we are supposed to integrate integration R x square dx dy. So let's just plug in the values. So if you observe that up till this point, let's name it as A. So this is point A. So the x is varying from, first let's just find out coordinates of A. So A is basically intersection of hyperbola and the line y equals to x. So that gives us y square is equals to 16, that is y equals to 4. We are taking it as positive because it is in upper half, like it's in first quadrant, so that's why we are taking y as 4. So if our y is 4, then our x is also 4. So point A is 4, 4. So if you observe that up till point A, our x is varying from 0 to 4 and our y is varying from 0 to x. Likewise, post this point A up till this point, let's say B, which is 8, I guess 2. So up till this point, our x is varying from 4 to 8 and y is varying from 0 to 16 by x. So let's just evaluate, like plug in the limits and see what's the value of shaded region. So area is, this thing is equals to integration x from 0 to 4 and from y from 0 to x square dy dx plus integration 4 to 8, that is x, and y varying from 0 to 16 by x square dy dx. So this simplifies to integration 0 to 4 x square into y limit from 0 to x dx plus integration from 4 to 8 and x square into y where limit varies from 0 to 16 by x dx. Now let's just simplify it. So it is equals to 0 to 4 x square into x dx plus integration from 4 to 8 x square into 16 by x dx. So that simplifies to integration from 0 to 4 x cube dx plus integration from 4 to 8 16x dx. So this is equals to x raised 4 by 4 and limit varies from 0 to 4 plus 16 into x square by 2 and limit varying from 4 to 8. So this is 1 by 4 into 4 cube minus 0 plus 8 into 8 square minus 4 square, that is 4 square, it will be 4 square, that is 16 plus 8 times 8 square, that is 64 minus 4 square, that is 16. So it is 16 plus 8 times 64 minus 16 will be 48. It is 4 raised 4, so it will be 64 rather than 16. So this term is equals to 448 units square. So that's the required area of shaded region, or basically the area of integral over the region R. And third says that evaluate the integral, that is this given integral, over region R, and the region R is basically rhombus formed with these vertices. So first let's just see the figure and see how we can solve it. So we are supposed to evaluate this integral, that is x minus y square cos square x plus y dx dy, and the region R is basically this rhombus that I am drawing. One vertex is pi comma 0, so let's say pi comma 0 lies somewhere here. Another is 2 pi comma pi, so 2 pi comma, let's say pi, this First is 2 pi comma pi, third is pi comma 2 pi. It will be somewhere here, pi comma 2 pi, and another point is 0 comma pi. That will be somewhere here, 0 comma pi. So let's join these points to see. So this is the region R over which we are supposed to evaluate the given integral. Now if you see that, we can do it directly as well, but then that will complicate our calculation. So first let's just do some transformation and reduce the integral basically to a simplified form. So let's use transformation as u equals to x minus y and v equals to x plus y. So if these are my u and v, then integration will be basically integration over the region r dash. R dash will be the region that will get post these transformation. U square cos square v into Jacobian du dv. Now let's just find out the Jacobian. That will be del u comma v with respect to del x comma y. So it is del u by del x, del u by del y, del v by del x, and del v by del y. So that simplifies to del u over del x will be 1, del u over del y will be minus 1, and del v over del x is also 1, del v over del y is also 1, and this Jacobian is 1 minus of 1, that is 2. So my integration reduces to integration over region r dash u square cos square v into 2 times du dv. Now I can pull out this 2 out of the integration signs, so it will be 2 times integration over region r dash u square cos square v into du dv. Now let's see what will be the change in these vertices of the rhombus post this transformation. So the transformation that I have used is u equals to x minus y and v is equals to x plus y, and the given points are pi comma 0, pi comma 0, 2 pi comma pi, and pi comma 2 pi, and further 0 comma pi. So when x is pi and y is 0, so u comma v reduces to, it will be pi comma pi. Likewise when x is 2 pi and y is pi, u will be my pi and will be 3 pi. Likewise when x is pi and y is 2 pi, u will be minus of pi and v will be 3 pi. And when x is 0, y is pi, u will be minus pi and will be pi. Now let's just draw the figure to see what area we get post transformation. So it will be, first coordinate is pi comma pi. Pi comma pi, let's say, lies somewhere here. Let's write it as pi comma pi. Second point is pi comma 3 pi. Pi and 3 pi will be, let's say, somewhere here. Another is minus pi comma 3 pi. So that is somewhere here. Minus pi comma 3 pi and minus pi comma pi somewhere. So now let's just join in these points to see the area that we'll get. So post transformation, our rhombus reduced to basically a square of length 2 pi. So this is square of length 2 pi. Now our integration basically reduces to integration over region r dash u square cos square v du dv, and it is equal to 2 times integration. V is varying from, if this is u axis and this is v axis, then v is varying from pi to 3 pi. pi to 3 pi v, and my u is varying from minus pi to pi, so it is u square cos square v du dv. Now if you see that the limit is basically constant, the limit of integration are not dependent upon u or v, so we can just separate them. So it will be equals to 2 times integration minus pi to pi u square du and integration pi to 3 pi cos square v dv. So this simplifies to u cube by 3 over minus pi to pi, and 2 times cos square v will be 1 plus cos 2v dv. So it simplifies to 1 by 3 into pi cube minus pi cube multiplied by v plus sine 2v divided by 2, and limit varies from pi to 3 pi. So this thing is equals to 1 by 3 into 2 pi cube times 3 pi plus sine 6 pi by 2 minus pi plus sine 2 pi by 2. Now if you know that sine 6 pi and sine 2 pi are 0, so this term reduces to 0 and this also reduces to 0. So we are left with 1 by 3 into 2 pi cube into 3 pi minus pi, that is 2 pi. So it is 4 pi raised 4 by 3. So that's the value of integration over the given region R. So that's the final answer. I guess we did some mistake. Yeah, here Jacobian is basically 2. So from here we'll get our dx into dy as 1 by 2 times du into dv, and what we replaced it as 2 times du into dv. Right, so it should be 1 by 2 here, and likewise 1 by 2, and it is 1 by 2 here as well. Okay, we used it 2, so it is 1 by 4, and this whole thing multiplied by 1 by 4, likewise this whole thing multiplied by 1 by 4 into 1 by 4. So our final answer is pi raised 4 by 3. So that's our final answer. You should be very careful while multiplying with Jacobian, otherwise your whole answer will be different, and these kind of mistakes are very common in exam. So let's move on to the next question. So the next question says that evaluate the integral. So they have given us an integral and we are supposed to evaluate its value. So the integration is from 0 to a, and x by a, this is basically limit of y and this is that of a, to x times dy by x square plus y square into dx. So let's just first evaluate it with respect to y. So it will be integration from 0 to a, x times tan inverse y by x into 1 by x, and limit varying from x by a up till a. So this is integration from 0 to a. If you see that this x balances out this, so it is tan inverse a by x minus tan inverse of x by a by x dx. It is x here, not a, so it will be tan inverse x by x. So this is integration from 0 to a tan inverse 1 minus tan inverse 1 by a dx. So tan inverse 1 is pi by 4, so it is 0 to a pi by 4 minus tan inverse 1 by a dx. So if you see that this term inside the integration sign is constant, so we can pull it out. So it will be pi by 4 minus tan inverse 1 by a and integration of dx over 0 to a, so that is x and limit varying from 0 to a, so it equals pi a by 4 minus a times tan inverse 1 by a. So this is the value of the given integral that is provided to us. So let's move on to the next question. So this question says that evaluate the given integration over region R, and the region R is defined by a parabola and 3 lines. So let's just draw the region R and see what is the bounded region R over which we are supposed to evaluate the given integral. So if this is x and y axis, so the hyperbola xy equals to 1 will be of form somewhat like this, and the line y equals to 0, this is y equals to 0, and y equals to x line will be somewhat like this, and another line is x equals to 2, that is this line. So the bounded region is basically the one that I am marking with blue color. So this is the region R over which we are supposed to evaluate the integral. So our integration is integration from over R x square plus xy dx dy. Now let's just find out the intersection point first. Let's name this point as A and this as B. So if you observe that A is basically intersection of hyperbola and the line y equals to x. So if y is equals to x and equation of hyperbola is xy equals to 1. So I'll use this relation here in equation of hyperbola. So that basically gives me x square equals to 1. So from here my x is basically 1. And if my x is 1, then my y is also 1. So my point A is 1, 1. Likewise, my point B is, on point B, x is equals to 2. So my y is basically 1 by x, that is 1 by 2. So B is 2, 1 by 2. 2, 1 by 2. Now let's just evaluate the integral. So if you observe that up till A, x is varying from 0 to 1. So up till A it is varying from 0 to 1, and y is varying from 0 to x into x square plus xy dx dy, plus after A, like in between A to B, x is varying from 1 to 2 and y is varying from 0 to 1 by x. X square plus xy dx dy. Now let's just solve this integration. So it will be equals to integration from 0 to 1, and we are first evaluating with respect to y. So it will be x square y plus xy square by 2 over 0 to x and dx, plus integration x equals to 1 to 2 x square y plus xy square by 2 0 to 1 by x dx. So it is equals to integration from 0 to 1. Let's plug in value of y. So it will be x cube plus x cube by 2 dx, plus integration from 1 to 2 x plus 1 by 2x dx. So it is equals to, if I integrate it will be 0 to 1, x cube plus x cube by 2 will be 3x cube by 2 dx, plus integration from 1 to 2 x plus 1 by 2x dx. So this is equals to 3 by 2 into x raised 4 by 4 integration from 0 to 1 plus x square by 2 plus 1 by 2 log x, and limit varying from 1 to 2. So it is equals to 3 by 8 into 1 plus 2 to the 4 by 2 plus 1 by 2 log 2 minus 1 by 2 plus 1 by 2 log 1. So if you see that log 1 is 0, so this term will be 0, and final result is 3 by 8 plus 2 plus 1 by 2 log 2 minus of 1 by 2, and that simplifies to, I can write minus of 1 by 2 as 4 by 8. So 3 by 8 minus 4 by 8 is minus 1 by 8 plus 2 plus 1 by 2 log 2, that is equals to 16 minus 1, that is 15 by 8 plus 1 by 2 log 2. So this is basically value of integral that we are supposed to find. So let's move on to the next question. So in this question we are supposed to prove that the integration, basically this integration which is integrated over region D, that is a unit disk, is bounded, that is it has upper bound as pi and lower bound as pi by 3. So our region that is given to us, that is region D, is basically a unit disk with center 0, 0. That is, let's say this be the unit disk, so this point will be 0, 1, it will be 0, minus 1, and likewise 1, 0 and minus 1, 0. Now if you observe that the integrand that we are supposed to integrate is fx, y is equals to 1 divided by under root x square plus y minus 2 square. Now if you observe that the denominator of this is, that is this x square plus y minus 2 square under root, this is basically distance of any point P, that is 0, 2, from any arbitrary point on the circle, from any arbitrary point on circle. So fx, y is basically reciprocal of this distance, right? So if let's say this is my point P, that is 0, 2. Now the minimum distance of this point P from the circle can be this, that is PA. Distance can be the minimum distance of this point P from the circle, and PB, if I take my point B as this, then PB will be the maximum distance of this point P from any point on the circle. So PA, that is equals to 1 unit, is basically maximum of f, maximum of under root, it will be maximum of under root, maximum of fx, y, because if when this distance PA is minimum, then only my f will be maximum. So and 1 divided by 3 will be minimum of fx, y, where x, y in both these belongs to the region D, that is the unit circle. So, and this is 1 by PA. Now if you observe that our integrand, that is fx, y, lies in between 1 and 1 by 3, because this is the minimum distance and this is the maximum distance. Now if I integrate this equation with over region D, so it will be integration over D 1 by 3 dA less than equals to integration over D fx, y dx dy, and integration over D dA. And we know that integration over region R dA is basically area of region R. So this is basically, if I take my R equals to D, that is unit circle, so area will be pi into R square, and since it's a unit circle, so radius will be 1, so it is pi into 1 square, that is pi. So let's just plug in the value in the above inequality. So that gives us 1 by 3 into pi less than equals to integration over d 1 divided by under root x square plus y minus 2 square dx dy less than or equals to pi, and that's what we are supposed to prove in this question. So let's move on to the next question. So the next question says that evaluate this integral by changing to polar coordinates, and hence show that this integration is equals to under root pi by 2. Okay, so in the question itself it has specified that we are supposed to use the polar coordinates to evaluate the given integral. So the given integral to us is integration from 0 to infinity e raised minus x square plus y square dx dy. We are supposed to evaluate this integral. This is the first part of the question. So polar coordinates are x equals to r cos theta and y equals to r sin theta. So in this case our Jacobian will be basically dx dy is equals to r dr d theta. So what you can do is, like, in order to save time in examination, you can remember Jacobian for a change in polar coordinates, cylindrical and spherical coordinates. So that comes handy while solving the question, as it's a 10 marker question. Had it been a 15 marker or 20 marker, then you can show like by calculating the Jacobian, but in 10 marker questions or less than that, you can directly use it. So the integral will reduce to integration from integration over first quadrant as our x is varying from 0 to infinity and y is also varying from 0 to infinity, e raised minus r square into r dr d theta. So this is equals to integration over 0 to pi by 2 and theta is r is from 0 to infinity, e raised minus r square r dr d theta. Now if I plug in r square is equals to 2, so that basically gives me 2r dr is equals to dt, and 2 from here I will say that my r dr is equals to basically dt by 2. So my integration reduces to 0 to pi by 2, 0 to infinity, e raised minus t, and r dr is dt by 2 into d theta. And since this integration is not dependent on theta, so I can just separate these double integral as 0 to pi by 2 d theta into integration from 0 to infinity e raised minus t dt by 2. Now this evaluates to pi by 2 into, it will be pi by 4 because I can pull out this 2 as well, e raised minus t by minus 1 and limit varying from 0 to infinity. So it is minus pi by 4 into, if I plug in infinity, it will be 0 minus 1, that is pi by 4. So this is the value of given integral that we are supposed to solve. Now in the question it further asks us to show that this is basically equals to under root pi by 2. So our claim is integration from 0 to infinity e raised minus x square dx is equals to under root pi by 2. Now if you observe that what we have just shown is integration from 0 to infinity e raised minus x square plus y square dx dy as pi by 4, but the term on left hand side can be written as integration from 0 to infinity e raised minus x square into e raised minus y square dx dy, and since the limits here are basically constants only, so we can write it as integration from 0 to infinity e raised minus x square dx into integration from 0 to infinity e raised minus y square dy, which is equals to pi by 4 that we just calculated. Now if you see that like x is just a variable. If I just plug in x y equals to x here in, so I'll get integration 0 to infinity e raised minus x square dx whole square as pi by 4. So this basically gives me integration from 0 to infinity e raised minus x square dx as under root pi by 2, and that's what I'm supposed to show in second part of question, that is this integral is equals to under root pi by 2. So now let's move on to the next question. So the next question says that they have given us a double integral and we are supposed to evaluate its value. So let's do that. So the integration that is given to us is integration from x equals to 0 to infinity and y varying from 0 to x, and x e raised minus x square y dy dx. Now first let's see the area over which we are supposed to evaluate it. So that will be x-axis, y-axis. So limit of x is varying from 0 to infinity, that is in this direction, like this whole region, and value of y is varying from y equals to 0, that is from here, to y equals to x. So the line y equals to x is this line. So the region over which we are integrating is basically this region. Now there are two ways to solve it. Either you can directly solve it, or what you can do is you can just basically interchange the limit. So if I interchange the limit, it will be y from 0 to infinity and x varies from y to infinity. X time, and we are integrating x time e raised minus x square by y dy. It will be dx dy this time because we change dx dy because we changed the order. So if we evaluate it, so let's just assume that x square is equals to t. So if my x square is equals to t, then 2 of x dx will be equals to dt, and the limit changes as t is equals to y square when x equals to y and t equals to infinity when x approaches infinity. So the integration reduces to y equals to 0 to infinity, and it is t is equals to y square to infinity e raised minus t by y, and x dx from here will be dt by 2 into dy. Now if I evaluate it, it will be integration from 0 to infinity. I can pull out 1 by 2 out of the integral signs, and integration of e raised minus t by y will be e raised minus t by y divided by minus 1 by y, and limit varies from y square to infinity dy, and it is equals to minus y by 2, limit varying from 0 to infinity 0 minus 0 minus e raised minus y dy, and this simplifies to 1 by 2 integration from 0 to infinity y into e raised minus y dy. And if you observe that this is basically gamma function, I can write it as 1 by 2 integration 0 to infinity y raised 2 minus 1 into e raised minus y dy, and it is equals to 1 by 2 gamma of 2, that is 1 by 2 into gamma of 1, that is 1 by 2, because gamma of 2 is 2 factorial. So the given integration is equals to 1 by 2. So now let's move on to the next question. So the next question says that evaluate this integration over the given rectangle and where the fxy function is defined as this. So we are supposed to integrate it over R, which is rectangle, and fx comma y dx dy. So first let's see what will be the region over which we are supposed to integrate. So region R is x varying from 0 to 1 and okay. So this is basically the required rectangle. And the region, basically the rectangle is, we read it as x varying from 0 to 1 and y also varying from 0 to 1. So this will be basically the rectangular region where this is 1 comma 0 and it is 1 comma 1. Likewise here it is 0 comma 1. Now fx comma y is x plus y if our y is in between this, and otherwise it is 0. So the integration basically is integration from x is varying from 0 to 1 and y is varying from x square to 2x square, and fxy in this region is basically x plus y, and it is dy into dx plus x varying from 0 to 1 and y varies from somewhere like apart from this region, it will be 0. So this whole integration will reduce to 0. So we are supposed to evaluate only this integral. So it will be x equals integration over x equals to 0 to 1 xy plus y square by 2 and limit varying from x square to 2x square dx. So it is integration over x equals to 0 to 1 x into 2x square minus x square plus 1 by 2 into 4x raised 4 minus x raised 4 dx, and that simplifies to integration from 0 to 1 x cube plus 3x4 by 2 dx, and it is equals to x raised 4 by 4 plus 3x raised 5 by 10 and limit varying from 0 to 1. So it will be 1 by 4 plus 3 by 10, that is 20, 5 plus 6, that is 11 by 20. So this is the value of integral that we are supposed to evaluate. So let's move on to the next question. So the next question says that after changing the order of integration of this, show that this is equals to pi by 2. Okay, so our claim is basically 0 to infinity sine mx by x dx is equals to pi by 2, and we're supposed to show this using this integration sign, like using this integration by changing its order. So the given integration is integral from 0 to infinity e raised minus xy into sine nx dx dy. Now after changing its order, it will be equals to integration from 0 to infinity e raised minus xy into sine nx into dy dx. Now if I evaluate it with respect to y, it will be integration from 0 to infinity sine nx into e raised minus xy divided by minus x, and limit varies from 0 to infinity dx. So it reduces to integration from 0 to infinity sine nx by minus x and 0 minus 1 dx. So it is equals to integration from 0 to infinity sine nx by x dx. Now we are supposed to, we have reduced the given integration in this form, but we are supposed to show that this is equals to basically pi by 2. Evaluate this, what we'll do is the original integration is basically integration from 0 to infinity e raised minus xy sine nx into dx dy. Now we know that e raised nix is equals to cos nx plus iota sine nx. So from here we can say that sine nx is basically imaginary part of e raised nix. So we'll be using this relation in this integration, so it will reduce to integration 0 to infinity imaginary part of integration 0 to infinity e raised minus xy into e raised nix dx and dy. Now this is equals to integration from 0 to infinity imaginary part of integration 0 to infinity e raised minus x y minus ni dx, and then integration with respect to dy. Now integration of this term will be basically 0 to infinity e raised minus x y minus ni divided by y minus ni, and limit varying from, it will be minus of y minus ni, and limit varying from 0 to infinity dy, and this is equals to 0 to infinity imaginary part of 0 plus 1 by y minus ni dy. Now it's to find out its imaginary part, first we need to rationalize it, so that basically gives us integration from 0 to infinity imaginary part of y plus ni divided by y minus ni into y plus ni dy, that is equals to integration from 0 to infinity, and its imaginary part will be basically n divided by y square plus n square, and integration with respect to y. Now this integration of this will be basically n into 1 by n tan inverse y by n, and limit varies from 0 to infinity. This n and this n balances out each other, and the final value reduces to tan inverse infinity minus tan inverse 0, and tan inverse infinity is basically pi by 2, and tan inverse 0 is 0 only. So we got our I as equals to pi by 2, but earlier we have shown that if we change the order of integration, this integral is equals to integration from 0 to infinity sine nx by x dx. So we have proved equivalence of basically these two integral, and that's what we are supposed to do in the given question. So this completes this question. So let's move on to the next question. So the next question says that evaluate the given integral. So they have given us an integral, and we are supposed to basically find out its value. So let us assume that given integral is I, and integration limit of y varies from 0 to 2, and that of x varies from 0 to y square by 2 y divided by x square plus y square plus 1 raised 1 by 2 dx dy. Now if we just draw the figure of the limits, so it is x is varying from, y is varying in between 0 to 2, and x is varying in between 0 to y square by 2. So if we just plot it, it will be y from 0 to 2, that is up till here, and x is 0 to y square by 2. So y square by 2 is equals to x. So its graph will be somewhat like this. But we are concerned only about the first quadrant. So the area that over which we are integrating is basically this. So let's just see how we can solve it. So it is equals to, so if you see that, like if we integrate first it with respect to x, then it will be too complicated. So first thing that we'll do is we'll just change its order of integration. So changing its order of integration, then if I change its order of integration, the limit varies from, basically x varies from x equals to 0 to x equals to 2, and y varies from y equals to 0 to, basically y varies from this point up till this point, that is y is equals to under root 2x to y is equals to 2. So let's change its order. So integration becomes integration limit of x from 0 to 2 and limit of y from under root 2x to 2 y divided by x square plus y square plus 1 raised 1 by 2 dy dx. Now if we just solve it, let's try to solve it first. So what we can do is we can assume the term in denominator, that is x square plus y square plus 1 is equals to u square, and if I just integrate it, differentiate it with respect to y, it will give me 2y dy is equals to 2u du, that is y dy is equals to u du. So my integration reduces to x equals to 0 to 2 and limit changes to, when y square is 2x, u is basically under root x square plus 2x plus 1, and when y is 2, so it is x square plus 5 under root, that is y dy is basically u du, and denominator we have u square is 1 by 2 dx. So this is equals to integration over x from 0 to 2 under root x square plus 5 minus x plus 1 dx. Now if we just take its integration, it will be equals to x by 2 under root x square plus 5 plus 5 by 2 into tan inverse, basically sine hyperbolic inverse x by under root 5 minus x square by 2 minus x, and limit varies from 0 to 2. So if we plug in the limits, we'll get and 4 plus 5 9, that is 3 plus 5 by 2 sine hyperbolic inverse 2y under root 5 minus 2 minus 2, and if I plug in 0, that basically gives me 0 plus 5 by 2 sine hyperbolic inverse 0 minus 0. This simplifies to 5 by 2 sine hyperbolic inverse 2 by root 5 minus 1 minus 5 by 2 sine hyperbolic inverse 0, and we know that sine hyperbolic inverse x is equals to log e x plus under root x square plus 1. So from here sine hyperbolic inverse 0 will be log 1, that is 0. So this term reduces to 0, and we need to check what will be the value of this term. So it will be 5 by 2 log 2 by root 5 plus under root 1 plus 4 by 5 minus 1, that is 5 by 2 log 2 plus 3 by under root 5 minus 1, that is 5 by 4 log 5 minus 1. So this is the final value of the integral that we were evaluating. So let's move on to the next question. So the next question says that evaluate the integral over the given region R, and R is basically a rhombus with these vertices. So we have seen this question. It is basically a repeated question. So the best way to do is to take some transformation, that is u equals to x minus y and v is equals to x plus y. That basically reduces the region R over v which we are integrating to basically a square, and that simplifies the calculation. So you restore to that method. So let's move on to the next question. So the next question says that evaluate this integral over this region R. So R is basically a rectangle. R is a rectangle with x line in between this region and y line in between this region. So if I plot my region R, so it will be somewhat like this: -1 1 0 2 2. So this rectangle basically denotes my region R, and I'm supposed to evaluate this. So the integration that I'm evaluating is double integral over R under root y minus x square modulus dx dy. Now if you see that in the given question they have used modulus inside the under root sign. So our function, if it is fx comma y, that is y minus x square, it will be equals to y minus x square when y is greater than x square, and x square minus y when y is less than or equals to x square. Now, so if let's just see what will be the how value of y changes. So first let's draw the graph of y is equals to x square. So it will be somewhat like this, it will be a upward opening parabola, somewhat like this. So y is greater than x square in the region, in this region basically. Y is greater than x square and y is less than x square in this region that I shaded with blue. And if you observe that the figure is symmetric around over y axis, so observe the graph or region over which we are integrating is symmetric along y axis. So it's enough to calculate the integral over this region, and then we can just multiply it by 2. So if we do it, then our integration will be basically, or we can just use the whole thing and we can vary value of x from -1 to 1 only. So integration will be, let us denote the region, basically this region as R1 and this region as R2. So integration over R of under root y minus x square modulus dx dy will be is equal to integration over region R1 under root mod of y minus x square dx dy plus integration over region R2 under root y minus x square mod dx dy. Now in the region R1, this is equals to under root y minus x square dx dy, and this thing is equals to integration over R2 under root x square minus y dx dy, and the limits are limit varying from x equals to -1 to 1, and over the region R1 y is varying from this, that is x square up till 2. that is y is equals to x square up till 2 under root y minus x square dy dx plus over region R2 x is again varying from minus 1 to 1 and y is varying from 0 to x square. Y is equals to 0 to x square under root x square minus y dx dy dx basically. Now if we integrate it, it will be integration from x equals to minus 1 to 1 and its integration will be y minus x square raised 3 by 2 times 2 by 3 and limit varies from x square to 2 dx plus minus 1 to 1, it will be minus 2 by 3 x square minus y raised 3 by 2 and limit varies from 0 to x square dx. So this is equals to, we can pull out 2 by 3 out of the integration sign, so it will be integration from minus 1 to 1 y minus 4 raised 3 by 2 minus, it will be 4 minus, sorry, it will be 2 minus x square raised 3 by 2 minus x square minus x square will be 0, so dx plus integration from, we can pull out minus 2 by 3 from here as well, it will be minus 2 by 3 integration from minus 1 to 1 0 minus x square raised 3 by 2 dx. So this will be equals to 2 by 3 integration from minus 1 to 1 2 minus x square raised 3 by 2 dx plus integration from minus 1 to 1 x cube dx. So that simplifies to 2 by 3 integration from minus 1 to 1 2 minus x square raised 3 by 2 dx and this will be x raised 4 by 4 and limit from minus 1 to 1, and if we just plug in the limits, this will basically reduce to 0, so we are supposed left with this integral only. And if you observe that the function inside the integral, that is 2 minus x square raised 3 by 2, it's an even function. So in case of even function, definite integral has a property, that is integration from minus a to a fx dx is equals to 2 times integration from 0 to a fx dx whenever fx is even and it is 0 when fx is odd. So using that property, it will be equals to 2 by 3 integration from 0 to 1 into 2 minus x square raised 3 by 2 dx. So it is, now to solve this, let us assume that x square is equals to 2 times sine square theta. So from here I will get my x as under root 2 sine theta. Now if I just calculate dx, it will be under root 2 cos theta d theta, and change in limit will be when x is 0. When x is 0, theta is also 0, and when x is 1, theta is pi by 4 basically, because sine square theta is equals to 1 by 2. That gives us sine theta as 1 by under root 2. So the integration reduces to 4 by 3 integration from 0 to pi by 4. 2 minus 2 sine square theta will be 2 cos square theta raised 3 by 2, and dx is under root 2 cos theta d theta. So if we simplify it, it will be 4 by 3 integration from 0 to pi by 4. 2 raised 3 by 2 into 2, that will be 4 only. So it is 4 times cos 4 theta d theta. Now we can write it as 8 by 3 integration from 0 to pi by 4, or maybe 4 by 3 into 2 cos square theta whole square d theta, and we know that 2 cos square theta is equals to 1 plus cos 2 theta. So if we use this relation here, we'll get it as 4 by 3 integration from 0 to pi by 4 1 plus cos 2 theta whole square d theta. Now that is equals to 4 by 3 integration from 0 to pi by 4, 1 plus 2 cos 2 theta plus cos square 2 theta d theta. Now if we further simplify it, it will be equals to 4 by 3 integration from 0 to pi by 4, 1 plus 2 cos 2 theta plus 1 plus cos 4 theta by 2 d theta. Here, like in this term, we have used this formula again, so that basically gives us this result. So if we further, like if we integrate it now, or first let's just simplify it further. So it will be 4 by 3 integration from 0 to pi by 4, 1 plus 1 by 2 will be 3 by 2 plus 2 cos 2 theta plus cos 4 theta by 2 d theta. So that simplifies to 4 by 3, 3 theta by 2 plus 2 into sin 2 theta by 2 plus sin 4 theta by 8 integration from 0 to pi by 4. Now if we plug in the limits, it will be 4 by 3 times 3 by 2 into pi by 4 minus 0 plus sin pi by 2 minus sin 0 plus 1 by 8 times sin pi minus sin 0. Now it simplifies to 4 by 3 into 3 by 2 into pi by 4 plus sin pi by 2 is 1, sin 0 is 0, and again sin pi and sin 0 both are 0, so this term reduces to 0. So our integration is pi by 2 plus 4 by 3. So this is the value of integral that we suppose, like that we are calculating. So this integration is equals to pi by 2 plus 4 by 3. So that's all for this video. We'll discuss other questions related to double integral in the next video. So thank you for watching, and please do like, share and subscribe the channel.